In this video, I'm going to talk about issues with using raw data as input to the particle classifier. In this image, which is a huge image of 2 micron by 16 micron size, so it is equivalent of 8 2 by 2 micron images. So we can analyze quite a bunch of particles in this huge image. And I'm only showing you a part of the image, not the whole. So as you see, I already have the protein DNA complexes masked. This is done through an automated script feature by using mask morphology. I discussed that in another video, so I'm going to go through that process. I already have the protein DNA complexes masked here, so I'm going to go through directly to particle classification. I have it already open in the background, and I already throw a bunch of junk particles into the trash. So we just go directly through the classification process. So as you see that the particles, the protein DNA complexes, they are presented here, and you can see the mask around the protein DNA complex. So that's the data, the masked area are the data that we use for our classification and alignment purpose. So here I'm going to go through a clustering analysis and see what are the issues. So click cluster, and so in this demo I'm going to use k-means because that's straightforward to understand. You simply specify how many groups or categories, here we just call them clusters, that you want for your final outcome. And to determine what is the optimum number for the our clusters, this is essentially a guess, right? And I can use testing, so I can sweep across these two parameters. So it is a range of the minimum number and the maximum cluster number. And it will generate this silhouette plot. And I'm going to avoid the technical details, which you can find in my thesis. And so basically, I want to use a local maximum for the silhouette mean, which is this blue line. Here I find the local maxima here, which indicates 5 is a good number to use for our cluster number. So I'm going to input 5 here as the number of clusters that we use for our clustering by using the k-means. Okay, I'm going to click OK, and it's generating 5 groups or 5 clusters here. So let's see how well it does. In our example, we are interested in the conformation of the protein DNA complex, mainly in how much the protein bends the DNA. So we are interested in the bending conformations. And that's what we traditionally analyze. Of course, we probably would also be interested in how the protein sits on the surface, whether it sits tall, like in this case, or whether it lays flat on the surface, right? So right now, as you can see, the first group, we have these two complexes, but the DNA bend angle are not the same. This is a bend state, and this is an unbent state. So while the proteins, they look similar, the DNA conformation is not the same. So Let's go to the second group. And you can see that, yeah, the first two, we already take the alignment, right? So it's aligned by its correlation to the template particle, which is the first one. It has a correlation number 1, and the number indicates how closely it correlates with the template, which is the first particle. So you can see the first two, they match pretty well, but then it goes to the third particle, which is the end particle, which has nothing to do with the first two, right? It looks nothing similar to that. And the fourth one is okay. Fifth one is an unbent state, so it's not similar to the first two. That's a bent state, right? And I have the last few, they are sharply bent, and they're not similar to the first two. So what does this tell us? It tells us that it's not good for analyzing or classifying the DNA bending conformations. So what it does is it classifies the particles according to their size of the proteins. So basically what the correlation does is it runs a cross correlation between two images, right? Or between two particles, right? And the cross correlation uses the intensity values or the raw data of the image as for its calculation. So you can imagine that the protein takes the largest share of the data because it's tall. That's why during the cluster analysis, it's classifying the particles according to the size of the protein primary, right? And not according to the shape of the band of the DNA. So, and we can quickly verify that by checking the parameters of each groups. For instance, in group 2, if I click the information panel, I can see the volume is 952 cubic meter, okay? If I click group 1, that's even larger, that's 1,000 cubic meter, okay? So it's actually classified them according to the size of the protein. And if we click group 3, then that's even smaller, it's 785 cubic meter. And the group 4, now you end up with smaller and smaller proteins, right? You can see that in the images. Now you have 638 cubic meter. So it's mainly classified them through the size of the protein or in the intensity of the image of the data input. And the DNA band state is secondary. So that's why it's not good for classifying DNA bending conformation. It's good for classifying the shape of the protein, such as how tall it sits on the surface, right? And that can affect its volume measurement. If the protein sits tall, the volume can expand to like 50% larger than when it sits flat on the surface. So this protein could be essentially the same size actually as like the proteins in group 3, which is a lot smaller than the group 1. They could be essentially the same size, it's only they sit differently on the surface. And that's because of the tip dilation effect of the AFM, right? If the protein sits tall, it dilates more, and that creates a big volume compared to when the protein sits low, even though they are supposed to be the same sized protein. They probably are, but the data that's output by the AFN would be different because of the tip dilation effect. That depends on how it sits on the surface. So this method, by using raw data as input, it suits best for analyzing the protein DNA complex according to its size. Let me show you here in this slide. So right. So if you have 2, 3 of these particles, right? So it matches first and foremost with the tau protein, but the DNA is basically secondary. Right? That's a match, even though DNA bending is different. This is an unbent state, this is a bent state. Because the proteins are both tau, so they say it's a match. But when for these two particles, you see the DNA band is pretty similar, but because the protein is different, right? This is a tau protein, this is a short protein. Even the DNA band stays the same, but the program says it's not a match. That's the issue that when we use the raw data as our input for the particle classifier. So that's not good for analyzing the DNA banding conformations. So what is the solution for that? To resolve these, we want to analyze the DNA banding conformations. So a potential solution for that is, instead of using raw data as our particle input, we can use the particle masks as our input to the correlation analysis, right? The benefit of using the particle masks is that it deprives the image of the raw data of the intensity data. So essentially you end up with a mask which is essentially 0 and 1. So it does not have the height information. So it only considers the two-dimensional shape conformation. So it does not consider the three-dimensional shape conformations. So in that case, only the 2D angle, right, the DNA banding conformation in the two-dimensional space are considered when we use the particle mask instead of using the raw data as our particle input. This is what I'm talking about by using particle masks as input to the particle classifier. The benefit of using masks is that it only uses 2D shapes such as DNA banding for matching, and disregard the height of the protein. So in this example, this is a short protein but with bent DNA, and it matches well with a tau protein with bent DNA. So the height of the protein doesn't matter. The DNA band state matters. And it does not match with the short protein but with the unbent DNA. So even though they are the same height of the protein, but the DNA band state is different, so that's why they do not match. So using masks as input to particle classification is good for classifying DNA banding conformations, but not so good for classifying protein conformations. So for our research interest, we would like to know the DNA banding states, and that's why we need to use the mask as our input. So how do we create these masks? So how am I going to create the mask that I just talking about? The way to do that, we need to use a technique called image math or image operation. So first we need to select a base image to create the mask from. And the base image we select is this modified height trace channel for our image. This is usually the one that automatically gets made by the system when you modify the surface, such as when you do the surface flattening or other surface normalization, filtering noise, so it automatically gets this modified height trace channel. Yes, when you perform those operations on the height trace channel, for example, then it gets a new channel called modified height trace. So we're going to use this data channel as our base image to create our mask from. Yes, so So we need to create a new channel, right? Out of this one. And to do that, we right click this channel and click duplicate current channel. And once that's done, we can perform the image math operation on the new channel, and that is in the modified tab. What the image math do is it can perform custom scripts, such as you can do all kinds of operations, such as addition, subtraction, like take absolute value or doubling, right? This is the image math part here. So let's examine what's here. So basically, we run custom code to perform manipulation of the data directly. The variable here is that we use is this IM, which is the image raw data. And this example code is simply doubles the image data, square each pixel values. Now we need to modify this to make our mask image, which essentially is a binary image, which 0 represents the unmasked area and 1 represents the masked area, right? We need to create a binary image for a mask image. Now, to create a mask, we need to know our mask threshold. So let's go back and check on the mask threshold that we're going to use. Yeah, let's see if the mask looks good or not. Let's zoom in this image. I can use the automatic one. And we need to mask the DNA. So we need the possible data we need to use above the surface background. So let's just reduce this mask a little bit. Let me see. It seems okay, a good value. We can probably reduce a little bit more. Let's see. We can reduce a lot more. Yeah, I think we're good. So let's take this value and use this to create our mask. So let's copy that number. It's 0.15 nanometer. Let's go back to the image mask dialog. And here I'm going to perform the operation. So to create a mask, we need to perform a logical operation. So any value that's larger than the value that we just used, right, is 1. So this is our logical operation, right? Anything smaller than this number will be 0, and anything larger than that will be 1. And we're going to use this logical image as our mask image. So when we click OK, it's going to create the mask image for us. Right. So now you get this binary image with 0 and 1. Okay. The DNA and the proteins are marked as 1, and the background surface is 0. That's the binary image we just created. Now we're going to this is the image that we just created, but as you see that the DNA is everything is highlighted, right? And we don't want the whole DNA or these free proteins. We only want the protein DNA complex, like a part of that, right? For our particle analysis, for example, like this, we don't need something like within this box. We don't need the whole thing. To do that, I need to use another technique that I discussed in another video. which is a custom script that automatically selects the protein DNA complex for us, right? It's a custom morphology script. Let's go back to our raw data because that script requires the raw data to perform. In order to mask the protein DNA complex without masking the whole DNA or the free proteins, we can use a custom script in the morphology operation. It's called mask protein DNA. I covered this already in another video, so here I'm just going to click this. And as you can see, the protein DNA complex are masked, and all the other noises are not masked. That's what we want, right? That's the particles we want. So then let's do the particle analysis. Click Analyze. Yes, we get the particles analyzed, and just to be clear, if we got the particles that we want, so we can do some visualization and see if they are the particles that we want to visualize. So there you go. And see all these protein complexes are exactly the ones that we want. And they're labeled, analyzed. Then what we can do is we can send them to the particle analyzer or to particle classifier. And I'm just going to send them to the particle classifier, and they can click select our particles. All right. And I've already done that. And of course, you need to perform a particle correlation analysis first. You click on that, and you will select the particle analysis with default crop size. And then here you would use the data used for correlation. Okay, this is important. By default, it's using the intensities. Okay, so you don't want the intensities. You want to use the mask. So that's in that way we only use the mask of the particles for our correlation analysis instead of using the raw data. Okay, we don't use the raw data, like I mentioned. Right? You need to use the mask. So that's why you pick up the option here. Pick out the mask. And this particle source will pick the default. Right? Particle analysis with default crop size. Then you click OK. Okay. This is going to take a while, and I already done that part. And let me just go directly to the particle classifier. And after you've done this particle correlation, just send these particles, analyzed one, right, to the particle classifier. So I already done that. Let's open that one. So here I have the particle classifier open for you. I already have all the particles correlated, and I manually pick those trash particles and throw them into the trash. So you already see this is the useful particles. Okay, that's what we're going to use them for our analysis. So this is what I'm showing you here is the modified high trace channel. This is not the data that we use for correlation. We use the binary image, the mask image for correlation. That's the duplicate channel here. Let's click that. So this is the binary image we created. So what we are essentially using for our correlation analysis is this masked area in red in this binary image. Okay, that's this mask These masks are what we use for our particle alignment and consequently for classification. So that's the real data that we use for our classification, as I mentioned earlier. So let's go back to raw data. We're going to do a clustering analysis and see how well this does, whether it resolves the DNA bending species better than using raw data, right? Uh, Currently we're using the masks for our correlation analysis instead of using raw data. Let's click cluster. We are going to use k-means for now because that's easier to understand. We're going to do some testing and see what's the optimal parameter we should use. We're going to sweep the parameter from 1 to 10 cluster number and see which cluster number gives us the best results. And it should give us a silhouette plot like this. Okay. Yeah, so we can see that so 9 and maybe 4 and 3, we need to use a local maxima as our cluster number. Yeah, if you want to know more about the technical details, like which number should you use, basically we need to use some number that has a higher silhouette mean value, which is this blue plot. You can read my thesis for more technical details. What's the best value we should use? We need to use the max, a number that a local maxima, right? That can give us a large silhouette mean value. So here right now it says the 9 is a local peak there, so we can use that number. And let's do that. So, well, the program says 9 is a good number. Let's do that. So we say 9 clusters. Let's click OK. So it's generating 9 groups or 9 clusters right now. And we're going to see how well it does the clustering. Start from group 1 and we just click alignment. So this is a band state. I think that's a pretty good job. So remember, it's using the particle mask for our correlation and alignment. So you are seeing is the raw data, but essentially what's calculating the back end, it is using this binary image, right? Two-dimensional binary image using the particle mask for our calculation and alignment. So it's aligning this red masks, right? It's not using the raw data. So that's what's happening in the back end. But this is useful for our DNA alignment, and it looks pretty good. So you can see this is a band state. I resolve this band angle species. Right? Let's turn to the next group. This one is, yeah, it's more like a 90-degree bend. Right, this one actually is a false positive, right, this one. But overall, I think it does a pretty good job. If it's a false positive, this is like essentially unbent state, right? 0 degrees. So we can just throw that into a new group. Yeah, we can, what I would do, I would rename this because I want to keep track of things. Let's say this is a 90-degree bend. And yeah, the second one may not be, but let's just do it for now. And the first one, I think it's maybe 30-degree bend, 45-degree bend. It doesn't really, yeah, this is not exact, like a precise angle measurement, so it's just roughly, right? it's a rough alignment. I mean, even if you do band angle analysis, you usually will have a broad distribution. Right? This you can imagine this is a broad distribution. This is a low band state essentially, right? What it tries to classify that. And this is like a more like a high band state, right? Let's turn to group 3. Now this is more like a a low band state, right? Yeah, I think it's probably a little bit smaller than 45 degree. Yeah, maybe 30 to 45 degrees close to unband state. Yeah, I think it does a pretty good job in getting the particle classes. Let's turn to the next group. Oh, this is the unband state. And these groups are sorted by its correlation. For example, this unband state, group 4, is similar to group 3, right, in some way. So if you sort the group 4 by its correlation, like you see, sort by correlation to this group. The group, okay, the group 3 comes not on top, but it's close enough. The group 6 probably is not unband state. So it's sorting by correlation to group 4. So anything that's close to conformation to group 4 will become on top, right? So now the group 6 is not an unband state. So that's group 4, 6, and 3, they are all kinds of unband states. So that's why they can belong to each other, right? Let's go back to sort by name. So we already examined group 3, 4, and the 6. Let's go to group 5. Group 5 is like a band state. Yes, let's say correlation to group 5. Yeah, 45 degrees, see? The 45 degree is closely related to group 5. This is like a band state, 45 degree. Yeah, I mean, we can just rename this. Let's say 45D. This is not a copy of this, it's similar to that. And we already say group 3 is unband state, right? Low band state is 40, maybe like 30 degrees something. Unband state is 0 to 30. Is it 0 to 30? Let's see. Yeah, there's some 0 degree. You probably have to separate them out. Some very low band state, would say. Yeah, it's a 30 degree or something. Let's rename that 30D. Alright, let's examine group 7. Group 7 is not a low band state, so let's say sort by correlation to this group. So it belongs to 45 degrees, so it's another 45 degree, a 30 degree. I would say 30 degree, so 30D. Let's say another group. You cannot rename them the same, so I just add a suffix. Alright, so we're almost done. So we have another 3 groups. Let's try this. Group 4 already done that as unband state. We can rename that as such as 0 degree. And group 6, yeah, we already done that, right? So it's 0 degree. Oh, we can rename them the same way, so I need to vary the name a little bit. Now group 10, I think it's the one that we throw out. Yeah, this is a false positive one. That should be 0 degree. So that's group 9. This is a highly band state. That's 135 degree. But this one is a false positive. This is belongs to 0 degree. I think it belongs to group 10. These are the hard one because, right, the way it is masked. I mean, there's no way to, you know, automatically classify. This is 135 degree. Let's do this. And finally, we have group 8. Yeah, that's another sharply bent state, above 90 or close to around 90, so I would say, right? So 90 degrees, not 90 degree. Yeah, so I mean, you can see that this process is pretty efficient. Um, it's not a precise angle measurement, but you get, you're not getting precise angle measurement anyway, even if you do a proper angle measurement, right? You only get a broad distribution. But for this purpose, even though each class we have some kind of a distribution of angles, right? Around 35, around maybe 45, or around 90. So, but it gets it pretty close. And even if you sort them, right? If I sort by 135 degree, and you can see it's sorted at 90 degree will come close to 135, right? So it's sorting this correctly, right? So it already gets the class very close to each other. So if I sort by the 30 degree, see 30 degrees, 30, 45 degree, 30 degree, right? So the program does a pretty great job, I think, in classifying the angular conformations of these particles. All right, what do you think? I think that's all for this video, demonstrating how to use particle masks as a potential solution to classify DNA bending conformations. So that's a very, I think, a powerful technique, especially for high throughput analysis, right? So if you have a lot of images, a lot of particles, you can do this very quickly, and the program can do the cluster analysis, and as you see, it clusters them very well. I don't have to do any manual job. I just check them, then name those classes, right? And it already does a pretty good job in resolving the different band state, right? So it's a very powerful technique that complements existing band angle analysis.